Hey guys, welcome back to a quick code. Today we're doing another Brainstellar Quant puzzle. This one is called Drunk and it's a hard problem. I'll let you guys pause and go with the problem once. So to explain the problem, we have an ant and it starts over here at this position. I'll denote it by an S, and it has to reach the opposite corner of the cube, which I'll be denoting by D. And this is the body diagonal, right? So it's like the very opposite corner that you can have on a cube. So the way the problem is stated, from each corner there are three. So for example, from this corner there are three possible edges we can go along, and the ant is drunk, so he doesn't really pick an edge smartly, and the probability of going along any one edge is 1 by 3, right? So there's a 1 by 3 chance of going along this edge, and this edge. So the ant can reach D from S in 3 steps, right? So let's say he takes a path of this, then this, as in this edge, and then this edge. Or you could also have considered this edge, then this edge, then this edge. So there's possibilities where the number of edges the ant travels to reach the opposite corner is equal to 3. If you think a bit more about it, so for example, if we consider the case of going along this edge, then going back along this edge, then taking this route, that would lead us to take 5 steps. And if you keep on thinking, then there's also cases where we can reach the destination 7 steps, 9 steps, and this goes on. And technically, there are cases where you're basically taking an infinite number of steps to reach the corner D, because technically the ant could just be looping around within a loop and never really reach D, right? But obviously the probability of these cases, so the probability of case 3 is the highest, and as we increase the number of steps that would have need to be taken to reach the destination, the probability decreases. So the probability decreases as the number of steps increase, right? So that's why if we were to calculate what is asked in the question, which is the expected number of steps to reach D from S, this would come out to be the probability that we are just going to take 3 steps into 3 plus the probability that we are just going to take 5 steps into 5, and this would come out to be an infinite summation, right? Basically I goes from 1 to infinity, 2i plus 1 times probability of 2i plus 1. But since this value over here keeps on decreasing, this would come out to be a constant value. And well, the question is to calculate this value, right? Now, there is a brute force approach that we could use, but I'm going to talk about that later on. First of all, we're going to go over a much more elegant solution. It is basically the solution given on the Brainstellar website. I'm just gonna try to give you guys intuitive hints and break down the approach for you guys, and then we'll talk about another brute force solution. So if we examine the symmetry of the cube and also with respect to S and D, well, this point, and this point are completely identical. Now again, this might not come instantly to you, so try to pause and really think about what I'm trying to say. From the POV of the cube, or from the POV of S and D, these 3 points, which are now I'm going to label as A, these 3 points labeled as A are completely identical. And I could say the same about these 3 points too, which I'm now denoting by B, right? Now, why is this? Well, each point marked as A is 1 step away from S and it's 2 steps away from D. And from any point A, there's one edge going towards S and the other 2 edges go towards B. And this is true for each and every point A, right? From each and every point A, one of the edges goes towards S and the other go towards a B mark point. And so we can give a similar argument for B points also. For each point B, it's 1 step away from D. It's always at least 2 steps away from S. And from S, there's always one edge going towards D and 2 edges going towards A, right? And notice how this is true for every point marked as B. So from the perspective of this problem, where we're just trying to calculate the number of steps that we need to take to reach a certain location given a starting location, and the way S and D are positioned, all of the 3 points A are completely equivalent and all of the 3 points B are equivalent. And the way the solutions to this kind of a problem works is to recognize that these 3 points and these 3 points can be grouped into equivalent classes. And just to reiterate what I've said earlier, the 3 points A are symmetric in the way that they're all 1 step away from S. They're all symmetric in the way that from any point A, one edge goes towards S and 2 edges go towards B. And they're also symmetric in the point of view that, well, for a cube, right, which has the S and D as marked as these points, these 3 points are always identical, right? Because They're like along the three axes of symmetry. And the exact same arguments can be done for the B points also. Now, the second hint I'd give you guys is, well, first of all, let's define some things. So if we try to calculate E of S, now what is E of S first of all? S denotes the number of steps required to reach D from S. And similarly, so if I would say the E of D, well, that's 0 because that is the number of steps or the expected number of steps required to reach D from D. And similarly, I can also define E of A and E of B. Well, E of A would just be the expected number of steps required to reach D from any point A, and B is also similar. You get the point. So yeah, so coming back to the hint, if we try to start calculating E of S, which is actually what we've been asked in the problem, this is the value that we have to give as our answer. If we relate E of S to E of A and E of B, then we might just be able to find an elegant solution to this problem. Because if we notice that from any point S, in one step we reach A, right? Because all of these points were A. So E of S is somewhat related to E of A, right? And we can integrate E of A into the calculation of E of S. And similarly, if we look for any point A, well, any point A has one edge going towards S and two edges going towards B. So that means that E of A can be related to E of S and E of B. And similarly, we can also try to create relations for E of B. So what I'm trying to say is, if we try to calculate all of these three values by relating them to each other, we might just come up with a very easy solution. So coming to the actual solution now. So if we were to calculate E of S, well, that's obviously going to be the probability of going along the first edge into the number of steps that it's going to take if we go along this route to reach D, right? And the same for the second edge and the same for the third edge, and right, so because these are the three possible cases. Well, first of all, since the probability of the first, second, and third edge is going to be 1 by 3, so this is something like this. But now let's talk about this thing, or well, actually this thing over here, right? The number of steps it's going to take to reach D, right? So coming back to the cube, so since on taking any edge from a state S, I reach a state A always, right? Now, if we were to talk about the expected number of steps it would take to reach D, well, I started with S, I took one step and then I reach A. And well, the expected number of steps is going to take, after we take this one step, it's going to take E of A, right? Because E of A is well defined as that very thing. E of A is the expected number of steps it's going to take us starting from position A to reach, sorry, this point is D, to reach D, right? So yeah, so to answer this particular case over here, the expected number of steps is going to take if we go along, let's say, this edge, well, that is going to be 1 because I took one step over here, plus E of A, because after taking that one step, I reach state A, and E of A is the very value that we defined as the expected number of steps it's going to take if we start at A to reach at D. So all of this means that E of S is equal to 1 by 3, let's say going along this edge, into 1 plus E of A, because we reach a state A from that edge, plus 1 by 3. Now this is considering the second edge. We can take this as the second edge. And in this case, we also again reach a state A. So that is also again going to be 1 plus E of A. Keep in mind that this value is the expected number of steps that we are taking in this particular case, right? And this is the probability of each case. And for the third edge, since again we are going to reach a state A, this is how it's going to look like, right? So if I just simplify this, this means that E of S is equal to 1 plus E of A, right? Similarly, if we try to calculate E of A now, right? Now, if we look at any point A, there's one edge, or sorry, two edges going towards B. So that is just going to be that 2 by 3 of probability into 1, because we have to take an edge, plus the expected number of steps it's going to take once we reach B, right? So this is this entire value is the expected number of steps it's going to take in these cases, plus a 1 by 3 probability that we take a step back in the wrong direction and reach S again. But since we took one step, it's going to be 1 plus E of S. And similarly, E of B calculated the same way. Well, E of B has one step going towards D, which means that in one step we reach the final destination. So that would look like 1 by 3, a chance of just taking a step and we reach the final destination, and 2 by 3 of a chance of going back to state A. So that would look like this. Now, we have 3 equations and 3 unknowns. So this is one equation, this is the second equation, and the third equation was this one over here, right? If we were to solve all these 3 equations, which is pretty trivial, we calculate the value of E of S as 10, which is the correct answer to the question. Now, to summarize, since we first clubbed equivalent points into classes or class of points, then we saw that from one class, on taking a step, we reached different classes, and hence we related E of, let's say, class 1, just to talk in general, E of class 1 to E of class 2, right? We used all of these tricks to create enough equations and to calculate all of the values E of any value x, just to be in general, right? Now, if you couldn't think of this approach that we just talked about, where we try to relate E of class 1 by using E of class 2 and E of class 3, there's another approach. It is also built upon the symmetry of the problem, but it's a bit more of a brute forcey type approach. So we now know that there are, well, in total 4 states that are possible. A state where you're 3 steps away from the destination, a state where you're 2 steps away from the destination, state where you're 1 step away from the destination, and the destination itself, which is D, right? Well, this was actually S, this was A, this was B, and this is D. Well, you get that already, right? So if we have these 4 states, and now we're gonna draw arrows to show going from one state to another, and the number I'm gonna write is the probability of going from this state to this state. So the probability of going from the 3-step state to the 2-step state is 1, because no matter what edge we take, we're always going to reach the 2-step state if we start from the 3-step state. Now, looking at the 2-step state, there's a 2 by 3 chance of going this way and a 1 by 3 chance of going this way. If we look at the 1-step state, there's a 1 by 3 chance of going this way and a 2 by 3 chance of going this way, right? Again, remember that the arrows denote the probability of going from state I to state J. Well, we can observe a few things over here. So first of all, if you try to pause and look at the system over here, we'll soon realize that it's always taking us at least 3 or more steps to reach the destination, right? And it's always in the form of odd number of steps. So 3, 5, 7, and so on. Now, why is this? Well, this is because at any point we can either stay. So let me call all of these steps as forward steps and all of these steps as backward steps, right? So at any point we either take a forward step or a backward step, and well, in the end the number of forward steps are gonna be equal to the number of backward steps plus 2 plus 3, right, in order to eventually reach D. So, and the total number of steps that we are gonna take in total is gonna be F plus B, right? Now I just proved that F is always gonna be B plus 3, because from any state we can either take a forward step or a backward step, and in total we're going to take 3 more forward steps than backward steps, because we eventually are going to end up at D, and the total number of steps is F plus B. So if I just plug in the value of F as B plus 3 over here, this comes out to be 2B plus 3, which denotes that the number of steps that we could take is 3 or 5 or 7 and so on. Now if we look at the probability of each case, so the probability of taking 3 steps, that comes out to be 1 into 2 by 3 into 1, right? Because it's basically 1 into 2 by 3 into 1. If we look at the probability of reaching D in 5 steps, well, there's 2 cases. Now, in order to reach in 5 steps, it's going to be the exact same as the case of 3 steps, but we'll also have to create one redundant loop. Or in other words, we'll have to make one back step. So we can create this back step or this back step. And for each of these back steps, we're going to also have to add an additional forward step, or the corresponding forward step. So for the case of this over here, it's going to be the case of 1 into the first kind of loop, which would be 2 by 3 into 2 by 3, and plus the other case, which starts off as a case of 3, but then we also have to multiply the other kind of loop, which would be 1 by 3 into 1. And if we look closely, this comes out to be the probability of 3 into 7 by 9. And if we try to calculate the probability to reach in 7 steps, it is basically the same thing. It's the probability that we reach in 5 steps, but again we also have to add the another logic of we have to create a loop of these steps or these 2 steps, right? So using the recursive logic, the probability of 7 is also gonna come out to be the probability of 5 into 7 by 9, because it's gonna look very similar to this case and this case over here. It's just that this is gonna be P of 5 and this is also gonna be P of 5. These 2 values are gonna be the exact same. So what we conclude is probability of n plus 2 steps is always gonna be the probability of n steps into 7 by 9. Well, since what we wanted to calculate was basically expected number of steps that we're going to take to reach t, this is going to come out to be p of 3 times 3 plus p of 5 times 5, as we've talked about earlier, right? And this is going to come out to be a sum which will look like this. And so if you know your math, then this is basically an AGP, and there are pretty standard ways of calculating an AGP or AGP sum. And if we were to calculate this using any standard approach, we come out with the value equals to 10, which is what we got earlier, which is the solution to the problem. I hope you guys understood both of these solutions. And comment if you want me to explain how you calculate an AGP sequence. I'll also do that if that is required. And I hope you guys understood the solution. And thanks for watching.